I'm going to have a look at question 45 in the assignment, which is an analog to digital conversion process. Here we have an LM35. The first instruction is for you to add the LM35 and give it a name TEMPR_sensor, short for temperature sensor. To do that, you go to the Devices tab, click on the LM35 and drag it over here. Once it's placed on the diagram, then you can draw to the particular pin you need to connect it to. Every student will be given a random pin. In this case, it's been chosen as C2. I've actually, for the demonstration purposes, connected mine to C5 for the moment, but you'll need to follow the instructions here. Do the same with a generic output device, give it the name fan and connect it to B1. So it will go from B1 to the fan. You'll drag that over and create that as well. In this case, for the demonstration, I've left it at B2. When you click on the temperature sensor, this little slider will appear and it will allow you to change the temperature. You'll notice that as I change the slider, the voltage here is changing. The LM35 is a linear device. At 0 degrees, it gives you 0 volts. Click on this once. Here we go, we are now at 2 degrees. We're getting 0.02 volts. 2 degrees, 0.02 volts. Click. Every time I click this, here we go, we're at 13 degrees. It's now giving us 0.13 volts. So I'll take this to 25 degrees. 25 degrees, and our temperature sensor will give us 0.25 volts. Let's have a look at our code. Our code is running at the moment. In function main, the first thing it carries out is an initialization of the ADC, and that's this function up here. Initialization of the ADC requires several things to be set, the first of which is the prescaler. ADC conversions cannot take place at the rate at which the microcontroller carries out its instructions, 16 megahertz in our case. It must be divided down so that it is less than 200 kilohertz. In this case, I've chosen a 125 kilohertz clock. So to get 125 kilohertz, I've had to set my prescaler to 128. And the data sheet will tell me that if I want a division of 128, I need to set those 3 bits high. The next thing that's part of my analog to digital conversion setup is to tell me which voltage reference I'm going to use. Here are the 2 bits that have to be set or cleared for the voltage reference. In this case, I want to use the internal 1.1 volt voltage reference. So I am setting both bits. You can see that in the data sheet as to how to set those. As part of initializing the ADC, I must enable it. The power to the ADC circuits within the microcontroller are turned off by default. This helps reduce power consumption when the ADC is not used. So to explicitly use the ADC, we must turn on the power to it internally. And then we need to do an initial conversion. The initial conversion for the ADC takes quite a long period of time relatively, and so we always do 1 to start with and we ignore that reading in the AVRs. This is a warning that's in the data sheet. So that's how you set up the ADC to do a conversion. I've done that once already. Now in my code, as I step around my code, here's my while loop. Do not change these lines of code. I want you to write the functions which are down here, not to change this. The first step is to read the analog to digital conversion. So what's going to happen here is it's going to jump up into this routine. It's going to set up my 80 mux, which is one of my registers. I'll come over here and have a look at my registers. And I can look at these 80 mux. This is the register here. The first thing it does is it sets 4 bits to 0. That's the effect of this line here. So those 4 bits in 80 mux here have been cleared to 0. The next step is to put the channel number into those 4 bits so that I know which channel I'm going to be reading. Come back here, toggle that so I can see it again, and I've put the number 5 into those 4 bits. So I'm reading channel 5. I've got to tell it which channel it is, and it puts it into ADMux. The next step is to carry out a to start a conversion. Conversions take a finite period of time. They take about 13 cycles at our 125 kilohertz clock. That means that I can do about 10,000 conversions per second, which means it takes about 0.1 of a millisecond to do a single conversion. So my microcontroller in this next line of code is blocking for that period of time in which the conversion takes. So what it's doing is, while the ADC is converting, this bit in the register is 0. When it finally goes to 1, then we have finished our conversion. So I block until that period of time. After that, my value will be returned in the ADC registers. So there's my ADC registers. You'll see that I have 2 registers because it's a 10-bit value. 2 higher bits are stored here, and the lower 8 bits are stored here. In this case, 25 degrees Celsius was converted to 0.25 volts, which is converted to an ADC number of 232. How did that work? We'll have a look at this diagram. Here's our LM35. At 25 degrees Celsius, we have 0.25 volts coming out. That goes into the analog to digital converter. It is compared in a simple ratio with 1.1 volts, and that's turned into a number from 0 to 1023. Very simple mathematical formula there to get 232. If, for instance, the temperature in the real world was 42 degrees, we would have 0.42 volts coming out here, would be compared to 1.1 volts, and the ADC output value would be 390. So that's what's happening here. Let's run this at a faster speed so we can see what's actually happening. Now I can look at the variables and see what is taking place inside memory. So I have, again, 25 degrees Celsius converted to 0.25 volts by my temperature sensor. That's converted to the number 232. When I change this to 42, got 42 degrees, 0.42 volts. It's now at 390. And that was the same as the calculation here. For 42 degrees is converted to 0.42 volts, which is then converted to an ADC reading of 390. Now I need to convert that back to an actual temperature, and you need to write the function in is here that will change the number 232 to 25, the number 390 to 42. In fact, I need this function to be correct from 0 to 99 degrees. So I go back to the instructions, and the instructions are here. You need to write what's inside that routine. I'll just put this into step mode. So this routine here, get temperature, takes in a 16-bit value, for instance 232 or 390 in a 16-bit form, and returns a value that represents the temperature. I've got it hidden here, you can't see what mine is doing, but you'll need to write your own. It's not exactly a linear process. You'll have to do a little bit of math with that. You may not use a math library. You must use integer manipulation here. And it has to be correct from 0 to 99 degrees. So as I run my program, and I go back to my variables, you can see that the output of this function is 42 degrees at 0.42 volts. And as I step this up, I can step it up to 66 degrees, which is 0.66 volts, and that is analog to digital conversion number of 613, and then that has to be handled by your function to convert it back to 66 for the degrees. and that must be valid all the way up to 99. So at 99, I've got 99 degrees, an ADC reading of 920, and these internal values are what's happening inside this function up here. If I put this into step mode, I can step through and see what's happening throughout my code completely. And you'll be able to step through your code and see what values are in memory, see what values are in your registers at any particular time. The second part and final part of the exercise is to make a routine that turns on the fan at or above a particular temperature and off below a certain temperature. So just read this clearly. Everyone here will have a different set of figures. In this case, the fan must switch on above 65. So at 64, it must not be on, and at 65, it must not be on, and at 66, it must be on. And then it must turn off below 49. So once it's turned on, it must come, as the temperature comes down, the fan will stay on. At 49, it will be on, and at 48, it will be off. In my code, I've created a couple of temperature settings here. 65 and 41 were the two values that I chose initially for my demonstration. As I run the program, I should be able to see that something happens around 65 and 41. So the fan is on at the moment, and as I decrease the temperature, (42) the fan stays on, 41 the fan stays on, 40 the fan went off. Now as I increase the temperature, the fan should not come on until it exceeds 65. It's at 65. When it exceeds 65, the fan comes on. So at 66, the fan comes on. So you'll need to set up that logic, and that all takes place in another routine that you have to write called control fan. You do not change any of this code. You change the code down here and create a couple of macros up here so that we don't have any magic numbers in our code. Hopefully that helps you understand what's required in this assignment question. Good luck with it.